So my name is Hendrik Lücke-Tieke from Fraunhofer. Today, my presentation will focus on the problem of finding interesting columns in tables that contain hundreds of columns. But before we look at the approach itself, I want to say a few words about the open data dialog workflow. So open data dialog has the goal to support the user in deciding which results satisfies their information need best. In many cases, high-level information is enough to decide whether the result is of interest or not, like the number of columns and rows or the natural language explanation that has been demoed earlier. But sometimes that information is not enough, so the users need to inspect results in detail or even have to compare various results to each other to decide. This can all be done in Open Data Dialog, an intuitive web application which borrows from the idea of online shopping. Users pick results that are interesting and bookmark them so they can be inspected and compared later in the process. The in-depth analysis is done in the Multi-Table Explorer module, which we also call Data Library. But what's the challenge here? So the challenge is results often contain hundreds of columns. I mean, literally also thousands. Feature subset selection alone is not the silver bullet here, because the interestingness of columns is not only dependent on the data, but also on the preferences of the user. But for the rest, I think I'll let my robot twin explain. So let's go. When dealing with flexible data retrieval systems like inode, it's common that the search results contain many attributes. From our 3 use cases, the astronomy use case contains the most attributes with more than 2,500 columns across 15 tables. In this demo, I show how degree of interest measures can help to cope with that many columns. We found an interpretation, and after inspecting it, we decide that it is indeed promising. We therefore bookmark it to add it to our data library. As we already have some other items in there, we now go to the library to compare all 4 interpretations at once. Here, all bookmarked tables are displayed below each other. Also, the columns are aligned vertically. The user looks at roughly 200 columns and 400 rows. Finding the information wanted in such a table is complicated and involves a lot of scrolling and searching. We approach this problem from 2 angles. First, we group similar columns to hide redundant information, and secondly, we sort columns by relevance to reduce the need for scrolling. Normally, spreadsheets display all columns available or cut off after a predefined limit. We chose a different approach here, which also contributes to the column ordering demonstrated later. The data library view analyzes the contents of each column and groups columns together if they are similar. Then only the most relevant columns of each group are being displayed while the rest is hidden. Of course, this can be undone on demand. For example, SpectroFlux R has been grouped with SpectroSynFlux R as they share almost identical distributions in value ranges. The user thus can compare search results faster, as they do not have to compare redundant information but can focus on the important differences. The second feature is a sorting of table columns based on the degree of interest. This degree of interest consists of separate measures quantifying whether a column contains useful information based on different questions. Questions like, does the column include much information by itself? Does it include much information about other columns with the same name? Does the column relate to the user query? Or is the column often requested by the user? The importance of these questions is different depending on the user's need for information. The minimap shows a small version of the data library view to help understanding the effects of degree of interest changes before applying them. In this example, we have 1 row for each interpretation, plus a top row for the groupings. Vertically, columns are sorted as currently displayed in the library view. However, hidden columns are also visualized. A light blue cell represents a low relevance value, while a dark blue, not visible, represents a high relevance value. The first measure is relevance, which is the data-driven measure based on the mathematical concept of entropy. The higher the entropy is, the higher the relevance of a cell will be. In this example, we might be only mildly interested in it and therefore assign it a rather low interest value, like 0.1. The second measure is comparison. It measures differences between columns that have the same name but originate in different interpretations. We keep its interestingness value at 0 as we are not interested in it currently. It is helpful in other scenarios where explicit comparison of column dissimilarities is of interest. Query overlap can be used to focus on specific contents. For example, an astronomer might be interested in the distance of galaxies. Then she would set the query to Z, as this is the domain-specific acronym for the distance measured by the redshift. Also, we set it to a high interest value to ensure that it is prioritized by the DOI algorithm no matter which group it is in. We observe that multiple occurrences of Z-related columns will have a high interestingness value. The fourth and last measure are the favorites. Setting the query is a convenient method to define interestingness in an ad hoc fashion, but users also have a priori interests that change only infrequently. We therefore included a configurable list of favorite columns that can be weighted separately. Here we set the interest to a reasonable value without overemphasizing it. When apply is clicked, groups are ordered by relevance and so are columns within each group. This leads to alternating blocks of dark and light blue, but in general this is only visible on the minimap as low relevance columns tend to be hidden in the data library view. As expected, Z columns are visible, while columns with a lower degree of interest are hidden. Interestingly, spectroflux measurements rank high and are thus visible, inviting to investigate further into this direction. To summarize, in this proof of concept we demonstrated how a mixture of data and user-driven interestingness measures can be applied to ease handling table visualizations with hundreds of columns. Users define their interest in certain aspects of the data explicitly and thereby steer the table layout. Although easy to learn and use, we would like to extend on it further to increase applicability. This includes examining the interdependence of DOI configurations and user tasks, and refinement of data and user-driven measures.